Somewhere beneath the rugged terrain of the Andes, the deserts of Nevada, or the highlands of Australia, the Earth holds one of its most timeless treasures, silver. For thousands of years, this gleaming metal has been mined, traded, and cherished. But today, silver is no longer just a symbol of wealth or ornamentation. It powers smartphones, solar panels, and even satellites. And to meet this modern demand, the silver mining industry has evolved into a sophisticated and highly technical global operation. But what does it actually take to extract millions of ounces of silver from the Earth each year? The answer is a fascinating blend of geology, engineering, chemistry, and brute industrial power. In this episode, we're going deep into the world of silver mining, from exploration to smelting and everything in between. Long before modern machinery and high-tech refining methods, silver captivated civilizations across the globe. Its shimmer adorned the crowns of kings and the coins of empires. The story of silver mining stretches back over 5,000 years, beginning in ancient Anatolia, modern-day Turkey, where early miners used stone tools to chip silver ore from cave walls. By 500 BCE, the Greeks were extracting silver on a grand scale from the laurium mines near Athens. That silver helped fund the Athenian navy, and in many ways, fueled the rise of democracy. Meanwhile, in the Americas, indigenous cultures like the Incas revered silver as a sacred metal, calling it the tears of the moon. Everything changed in the 16th century, when the Spanish conquest of the New World unlocked vast silver deposits in Potosi, in present-day Bolivia. At its peak, this one mountain produced so much silver that it funded half of Europe's economy. But that wealth came at a brutal cost. Millions of indigenous and African slave laborers toiled under horrific conditions to meet colonial demand. As centuries passed, silver mining spread across continents, from the Comstock Lode in Nevada during the American Wild West to high-tech operations in Australia, Canada, and China today. Each era brought new tools, new challenges, and new understandings of both silver's value and its consequences. What hasn't changed is our fascination. Silver is more than a metal. It's a mirror reflecting human ambition, ingenuity, and at times exploitation. And as we explore how silver is mined in the modern era, we carry the weight of that legacy with us. The journey begins long before a single rock is moved. It starts with exploration, weeks, months, and sometimes years of geologists combing through remote mountain ranges and deserts in search of silver-rich deposits. Using a combination of geological surveys, satellite imaging, and exploratory drilling, they search for the telltale signs of mineral veins hidden deep underground. Once a promising site is found and test samples confirm sufficient silver content, a mining plan is drawn up. Environmental permits are secured, infrastructure is developed, and massive equipment begins to move in. Now, it's time to dig. Depending on how deep the silver deposit lies, mining operations take one of two routes. If the silver is close to the surface, open-pit mining is the method of choice. This involves stripping away layers of earth, known as overburden, to reveal the ore beneath. Massive shovels and dump trucks haul out thousands of tons of rock each day, carving a giant staircase-like pit into the ground. If the deposit lies deeper underground, things get more complex. Vertical shafts are drilled straight down, and horizontal tunnels are carved through solid rock. Workers navigate a maze of passageways, often more than a mile beneath the surface, using drills and explosives to break apart ore. Whether surface or underground, the goal remains the same: bring silver-bearing rock to the surface as efficiently as possible. At this stage, the ore still looks like nothing more than ordinary rock. In fact, each ton of raw material might contain just a few grams of silver. To get to the metal locked inside, the ore is trucked to a processing facility, where it undergoes a powerful mechanical transformation. process starts with crushing. Giant jaw crushers bite down on the rocks, reducing them to chunks the size of baseballs. Those fragments then pass through secondary crushers, getting smaller and smaller until they resemble gravel. But to truly release the silver, the material needs to be pulverized. That happens inside large rotating mills filled with steel balls. As the mill spins, the ore is ground into a fine gray powder, similar in texture to flour. Only now is the silver ready to be separated chemically from the waste. With the ore reduced to powder, it's time for science to take over. The method used depends on the type of rock and how the silver is embedded. If the silver is found in sulfide minerals like galena or chalcopyrite, the ore goes through a process called froth flotation. In large tanks, the powdered ore is mixed with water, air bubbles, and a cocktail of chemical reagents. As the mixture churns, silver-containing particles attach to the air bubbles and rise to the surface, forming a foamy layer that can be skimmed off. What's left behind is mostly waste. If the silver is embedded in oxidized rock, a different technique is used, cyanide leaching. Though controversial, this method is highly effective. The ore is soaked in a weak cyanide solution, which dissolves the silver into a liquid form. That solution is then filtered, and the dissolved silver is extracted using zinc or activated carbon. Whichever method is used, the result is a concentrated form of silver. Still not pure, but now in high enough quantities to be economically viable. With the concentrate in hand, the next step is smelting, an ancient process brought into the modern age. The concentrate is shipped to a specialized facility where it's heated in furnaces that can reach temperatures well over 2,000 degrees Fahrenheit. At these extremes, the silver melts and begins to separate from the impurities. Fluxes like silica or lime are added to help the process. They bind to unwanted materials, which float to the top as a thick layer of slag. The heavier silver sinks to the bottom, forming a molten pool of metal that is then poured into molds. As it cools, the silver solidifies into rough ingots, still containing traces of other metals like copper or lead. To reach the high purity levels needed for commercial use, the silver must undergo one final critical stage: refining. Refining begins with electrolysis. The rough silver ingots become anodes, electrodes that dissolve when electric current is applied. They're suspended in a tank of silver nitrate solution, alongside thin sheets of pure silver, which act as cathodes. As electricity flows, silver atoms from the impure anodes dissolve into the solution and redeposit themselves onto the cathodes in pure form. Over the course of several days, these cathodes grow into thick, gleaming sheets of high-purity silver. Meanwhile, any impurities either fall to the bottom of the tank as sludge or remain suspended in the liquid. The refined silver is then melted once more and poured into standard bars, each one stamped with its weight, purity, and a unique serial number. Some of these bars are headed to bullion vaults and investors. Others are destined for industrial plants, where they'll be turned into wires, mirrors, circuits, and connectors. Once refined, silver enters the global economy through a complex and high-security supply chain. Each bar is carefully weighed, tested, and sealed in tamper-proof packaging. From there, they're shipped to precious metal exchanges, manufacturers, and refineries around the world, often under armed guard or with GPS tracking. The applications are nearly endless. In smartphones, silver conducts electricity with unmatched efficiency. In solar panels, it converts sunlight into clean energy. In hospitals, it acts as an antibacterial coating. And in jewelry, it dazzles and endures. Every ounce of silver may look the same to the naked eye, but the journey behind each bar spans continents, cultures, and centuries of human progress. Silver isn't just a precious metal, it's a story of discovery, transformation, and relentless ingenuity. And now, you know how millions of ounces of it are mined, processed, and put to use, one shimmering bar at a time. Thanks for watching. If you love learning how everyday materials are made, from the mines to the machines, hit that subscribe button and join our growing community. We've got more incredible journeys coming your way, from the heart of the earth to the hands of innovation. In the modern world, stainless steel pipes are everywhere. From chemical plants to skyscrapers, from food processing to medical equipment, these gleaming tubes carry the lifeblood of industry: water, gas, steam, and chemicals. Strong, corrosion-resistant, and built to last, stainless steel pipes are the unsung heroes of modern infrastructure. But how do you turn raw steel into perfectly round, polished pipes that can withstand extreme pressure, heat, and chemicals? In this video, we'll take you inside one of the world's leading stainless steel pipe manufacturing facilities, where science, metallurgy, and engineering come together to produce one of the most dependable industrial components ever made. From melting and casting, to rolling and welding, to polishing and testing, we'll uncover the incredible journey of stainless steel pipes, from raw materials to high-performance products. Let's begin. Everything begins with raw materials: iron ore, nickel, chromium, and other alloying elements. Stainless steel isn't just regular steel, it's a carefully balanced alloy designed to resist rust and corrosion. The two main elements that make stainless steel so special are chromium, adds corrosion resistance. Nickel adds strength and improves performance at high temperatures. These raw materials are delivered to the factory in bulk, either as refined metal pellets, scrap stainless steel, or pre-alloyed forms. In addition to virgin metals, stainless steel production heavily relies on recycled scrap metal. In fact, over 60% of the input materials often come from recycled stainless steel or carbon steel. This scrap is collected from old machinery, decommissioned equipment, cuttings from manufacturing plants, and even used consumer products. Using recycled steel not only saves raw material costs, but also significantly reduces the environmental footprint of stainless steel production. Once loaded into the furnace, the recycled and virgin metals melt together into a uniform alloy, ready to begin the next chapter of their industrial life. Once in the plant, the raw materials are loaded into massive electric arc furnaces or induction furnaces. These furnaces can reach temperatures over 1,600 degrees Celsius, 2,900 degrees Fahrenheit, hot enough to melt all the metals into a glowing molten bath. The exact mix of elements depends on the grade of stainless steel being produced. For example, 304 and 316 are two common grades used in everything from kitchen equipment to marine piping. The molten steel is sampled and analyzed using spectrometers to ensure the chemical composition is within specification. If not, adjustments are made: more nickel, less carbon, or a touch more molybdenum to fine-tune the alloy. Once perfected, the molten steel is poured into molds to form billets or slabs. These solid metal blocks are the starting point for rolling stainless steel sheets or forming pipes. After cooling, the billets go through a process called scarfing, where surface impurities are removed using torches or grinding tools. Clean surfaces ensure the quality of the final product. These billets are then reheated in a furnace and passed through massive rollers to form long, thin strips of steel called hot-rolled coils. These coils are then pickled in acid to remove scale and cool. From here, the steel strip is ready for transformation into pipe. Now that the steel coil is ready, it moves to the forming line, where flat steel becomes a round pipe. There are two main methods to produce stainless steel pipes: seamless pipe manufacturing, welded pipe manufacturing. To make seamless pipes, a solid round billet is pierced in the center using a rotary piercing mill. This creates a hollow center while maintaining the material's strength. The billet is then elongated and rolled through a series of mandrels and rollers, gradually increasing the length while reducing wall thickness. Because there is no weld, seamless pipes are ideal for high-pressure applications like oil and gas pipelines. However, they're also more expensive to produce and limited in length. Welded pipes begin with a flat steel strip, called a scalp, uncoiled and straightened. The strip passes through a series of rollers that gradually shape it into a cylindrical tube. At the point where the edges meet, high-frequency electric current is applied. This creates heat and fuses the edges together, forming a strong longitudinal weld. This is known as electric resistance welding, or ERW. After welding, the pipe is immediately cooled and passed through a sizing mill, where final dimensions are achieved and roundness is perfected. The weld seam may be left intact or further processed. For high-specification pipes, the inner weld bead is removed using scarfing tools, and the weld zone is heat treated to normalize grain structure. Whether seamless or welded, all pipes are then straightened, cut to length, and labeled for further processing. After forming, stainless steel pipes undergo heat treatment, also known as solution annealing. This step relieves internal stresses, improves corrosion resistance, and restores ductility. Pipes are passed through a furnace heated to 1050 to 1150 degrees Celsius, 1920 to 2100 degrees Fahrenheit, depending on the grade of stainless steel. Once they reach the desired temperature, they're rapidly cooled, usually by immersion in water. This prevents the formation of carbides, which could otherwise weaken corrosion resistance. After heat treatment, a thick oxide scale forms on the pipe's surface. To remove it, the pipe undergoes pickling, an acid treatment using nitric and hydrofluoric acids. The pipes are submerged in acid baths or sprayed in a closed system, where the scale dissolves, revealing the bright silver finish underneath. After pickling, pipes are rinsed, dried, and inspected. This step is essential to restore the corrosion-resistant surface layer called the passive layer, which protects stainless steel in corrosive environments. Next, the pipes go through final shaping and finishing. First, the pipes are measured for outer diameter, OD, wall thickness, and straightness using laser measurement systems. Pipes that don't meet tolerance are rejected or reworked. Then comes cold sizing, where pipes are passed through dies that bring them to exact specifications. This improves dimensional accuracy and enhances surface finish. Following sizing, pipes move through a straightening machine that uses multiple rollers to apply pressure from various angles, ensuring perfect alignment along the pipe's length. Polishing comes next, depending on the application. For industrial use, a brushed or matte finish may be acceptable. For decorative or food-grade applications, pipes are polished to a mirror-like surface using abrasive belts or buffing wheels. Polishing not only improves appearance, but also enhances cleanliness, important for medical, pharmaceutical, and food processing industries. Some pipes may also receive passivation, a secondary acid treatment that strengthens the protective chromium oxide layer on the surface. At this point, pipes are dimensionally accurate, polished, and protected, but they're not ready to ship just yet. To ensure every pipe is safe, reliable, and defect-free, manufacturers perform non-destructive testing, NDT. Depending on the pipe's end use, testing may include eddy current testing, detects surface and near-surface flaws using electromagnetic fields. Ultrasonic testing sends high-frequency sound waves through the pipe to detect internal cracks or inclusions. Hydrostatic testing fills the pipe with water under high pressure to check for leaks or weak spots. Visual inspection. Experienced inspectors look for scratches, dents, or weld irregularities. Dimensional verification. Pipes are measured for wall thickness, diameter, and ovality. Every test is documented and traceable. Pipes that pass are marked with traceability codes, indicating heat number, grade, dimension, and test status. In high-purity applications like semiconductor manufacturing, even more stringent testing is done, checking for chemical leachability and ultra-smooth internal finishes. Defective pipes are either recycled or repaired. The goal is simple: zero compromise. With all tests passed, the stainless steel pipes are ready for shipping. First, the pipe ends are often beveled, threaded, or capped, depending on the customer's requirements. Then, pipes are grouped by size and wrapped in bundles using steel straps or protective film. For international shipments, pipes are coated in rust inhibitors and sealed in plastic sheeting. Each bundle is tagged with complete specifications: grade, length, wall thickness, heat number, and destination. Shipping stainless steel pipes requires care. Even a small scratch can become a corrosion site, so manufacturers take extra precautions with foam padding, separators, and even wooden crates for high-end products. From here, pipes are loaded onto trucks, ships, or trains, ready to support construction, energy, and manufacturing projects around the globe. From deep underground pipelines to towering skyscrapers, stainless steel pipes make our modern world possible. Behind each one is a story of science, precision, and durability, of molten metal forged into form, polished to perfection, and tested for the harshest conditions on Earth. It's easy to take them for granted, but once you've seen the effort, care, and technology behind each pipe, you realize stainless steel isn't just metal, it's trust in physical form. Thanks for joining us on this journey through the stainless steel pipe factory. If you enjoyed this video, make sure to subscribe for more deep dives into how the world's most important materials are made. And as always, stay curious.